for giving me the possibility of speaking here, this nice conference. I was trying to find a subject which is close to the thematic of the conference, and I decided to speak about geometry of quantum mechanics. This is a rapidly developing subject, but usually when related to quantum optics, quantum information, etc., this is usually based on finite dimensional Hilbert spaces. Here I want to introduce the infinite dimensional picture. Hilbert spaces, of course, if quantum mechanics is concerned. Therefore, there will be no problems with dual, pre-dual, blah, 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 yeah, because everything will be Hilbert. Some of Hilbert spaces will be real, but this is also, of course, abstract complex Hilbert space has no canonical, so to say, realization, but in acting examples, this is also so. For instance, if you consider L-square functions, then of course you can reduce to consider only real functions, etc. This talk is based on an old paper. This is not completely this paper, but it's based on some ideas presented in a paper with Beppe Marmo, Marek Kusz, and Tatiana Szulno. Okay, so I will repeat many of what has been already said during this conference. First of all, partial differential equations are, in geometrical terms, certain submanifolds of Z bundles. A particular case of ordinary differential equations is associated with a tangent bundle, which is the first jet of curves on a manifold N, and implicit first-order ordinary differential equation, which in mechanics is called implicit dynamics, is just a submanifold. Of course, you can consider also more general subsets. Then, of course, your equation will not be smooth or etc., but still makes sense in many cases. So, implicit first-order differential equation has well-defined solutions. Yeah? So solutions are curves in the manifold N, such that the tangent prolongation belongs to D, to this submanifold describing the dynamic. So the curve is called admissible if it is the tangent prolongation of its projection. So to consider solutions or admissible curves in Tn is actually the same. Yeah, because on N, the solutions of the dynamics are projections of admissible curves onto the manifold. Of course, there is the best known example are explicit differential equation, and this is how usually people understand ordinary differential, first-order ordinary differential equations, that they are defined by vector fields. Yeah? So vector fields define the equations, they are trajectories of these vector fields. And this fits exactly into this picture, because if you consider the image of the vector field, consider it as a section of the tangent bundle, so in coordinates, if these are coefficients in this vector field, so it takes this form in adapted coordinates. And of course that the curve gamma on n has prolongation, tangent prolongation to the dynamics, this one, means exactly this equation. So this is the standard equation for trajectories of this vector. Not, however, that in this implicit case, different implicit differential equations may have the set of solutions because, first of all, of course, it makes sense only consider those points on the manifold which are elements of the projection of the dynamics. Yeah, because outside we cannot construct any solution. So this gives certain integrability condition. The first one, say, integrability condition for implicit differential equations. So we should intersect dynamics with the tangent of the projected submanifold, and so on. So, of course, a priori, this procedure may be infinite, but in our cases, this will finish in the first step. So. Yeah, so of course, solving, so I will speak about this Tulczyjew approach to mechanical systems. And no, the first step is to understand that this dynamic is generally implicit, not given by a vector field. And this Tulczyjew method, Tulczyjew triple, separates two problems concerning with mechanical systems. One is constructing dynamics out of the data, I mean Hamiltonian, Lagrangian, etc., which is purely a geometric procedure. The second, of course, is to solve these equations we obtain implicit, which is generally a difficult task. But as usually differential equation, this is completely separate task. Yeah? One point is to write down the equations, the other point is to solve them. And usually you have used particular methods for each of the equations, yeah, because they are very different. They behave very different. So, of course, in mechanics, this is a symplectic form in Hamiltonian mechanics who makes the picture working. So if I have a two-form, the two-form I will understand as a morphism of vector bundles tangents to cotangent bundle. And the standard canonical symplectic form of the cotangent bundle has this well-known form in the Darboux coordinates. So P's are momenta, Q's are positions in the manifold. There are different conventions, of course, but if you use one convention in definition of canonical omega Q, then you should adapted convention defining Hamiltonian vector fields, etc., etc. The Lagrangian submanifolds in symplectic manifolds of dimension 2n is submanifold of dimension n on which the symplectic form vanishes. I mean, I restrict symplectic form to the submanifold and it should give 0. Instead of saying that this is of dimension n, I can say that this is maximally with this property, so maximally isotropic. A well-known example is the image of a one-form in the cotangent bundle. So this image of a one-form is Lagrangian submanifold, if and only if eta is a closed form. Yeah, and this is for exact eta, this is elementary proof that this is really works, yeah, because here this is Q-symmetric and this is symmetric, yeah, so this gives some. I use, of course, Einstein summation convention. So Hamiltonian mechanics, which is actually the easier part of this Tulczyjew picture, is the standard one, namely with the Hamiltonian H, which is a function on n, undefined via this symplectic form isomorphism. With dH, I associate a vector field, which is called Hamiltonian vector. Noted that I don't use brackets, yeah, because the brackets, as what I really need is this much omega position. Yeah. And locally Hamiltonian vector fields corresponds to closed forms. If this form is exact, it is Hamiltonian and has a single Hamiltonian. Another important observation is that if I have a symplectic form on a manifold N, that there is a canonical way of lifting. Actually, you can lift any tensor field. But this is particular case that I can lift symplectic form from N to Tn. And this is canonical procedure. And the obtained form is also symplectic one. So in Darboux coordinates, it looks like that. This is like formally differentiating with respect to time, so to say. Yeah? And a simple observation is that the vector field on N, the section of the tangent bundle, is locally Hamiltonian, and is here a symplectic manifold. So it is Hamiltonian if and only if its image is a Lagrangian submanifold in this tangent bundle with the lifted symplectic structure. So there are various equivalent ways to work with the same concept. Therefore, by generalizing Hamiltonian system on a symplectic manifold, I will not understand just a Hamiltonian vector field with a given Hamiltonian, but just a Lagrangian submanifold in this manifold. This could be implicit, could be like that, yeah, in the projection. So Kasia already presented this example, but let me show it once more in the case of massless particle. So this mass shell is in this example just a cone, light cone. So this is the equation of this cone. I don't assume this is Minkowski. This could be a metric, yeah. And these are equations known from relativistic mechanics for a massless particle, free massless particle. You see, there is no chance that this dynamics is given by a Hamiltonian vector fields, because there is this constraint which prevents from that. This is not defined over the whole Lorentzian manifold, space-time in our case. But this is, of course, one of the principal examples. So, but using this idea of Tulczyjew, it is possible to obtain this about dynamics from a constraint Lagrangian or constraint Hamiltonian. Yeah? So how constraints canonically appear in the framework of mechanical systems. Okay, so let's go back to this Tulczyjew triple. So Kasia has already written it many times. So I start with a symplectic form canonical on the cotangent bundle, interpreted as this isomorphism. We know this is isomorphism of double vector bundles. And we have a canonical isomorphism between this serves for general vector bundle between T star E star and T star E, if E is a vector bundle. This is canonical isomorphism of double vector bundles. But in our case, where E is just Tm, in the adapted coordinate, this is just represented locally by this permutation of coordinates. So finally, we get this picture, which consists of isomorphism of double vector bundles. We have 3 of them, which are simultaneously symplectomorphism. Sometimes one uses one of it being anti-symplectomorphism, but if Lagrangian submanifolds are concerned, this plays no role. So this part, this is T star M is a phase space. So okay. So maybe I will pass to next slide. So this is, instead of textbook on Lagrangian and Hamiltonian mechanics, you can show your student this one picture and say, okay, we have these isomorphisms, which are symplectomorphisms, canonically. T star M is our phase space, and the dynamic, through physically meaningful dynamics, is a phase dynamic, not Euler-Lagrange equation. The dynamics is phase dynamics. Of course, from phase dynamic, you can obtain Euler-Lagrange equations, losing some information. However, this information tells you how velocity are associated, so how momenta are associated with velocities, which is physically important information. So if I have Lagrangian as a function on this dynamically configuration space, then of course you differentiate it. The image of DL, as we already know, is a Lagrangian submanifold. So I go back with this map alpha, which is symplectomorphism, and I obtain certain D as an implicit dynamics. This is exactly the phase dynamics of this Lagrangian. I want to stress that we don't assume any regularity conditions for this Lagrangian. So this Lagrangian need not to be regular. On the other hand, we have the same picture. We have a Hamiltonian on the phase space. DH go here, and we go here to obtain a priori different dynamics, yeah? D. So, but in this case, this is exactly the image of the Hamiltonian vector field. If we start with one Hamiltonian, Kasia told you that there are some generating families which are more general approaches to this. So these are 2 ways of obtaining dynamics out of Hamiltonian or Lagrange. So the right-hand side of this picture is Lagrangian. This is the recipe for obtaining the dynamic. The left-hand side is Hamiltonian with similar recipe. In both cases, D, which can be different in both cases, is a Lagrangian submanifold in T star M, representing the dynamic. And this is the same D, if and only if our Lagrangian is regular. I mean, in this case, you can find a Hamiltonian which gives you the same D.
Means in this context?
Regularity means that the vertical derivative of Lagrangian is isomorphic. So you see, on Kaja's picture, this was denoted with small lambda. This is a map from T and 2 star M, which should be diffeomorphic. Then, of course, if this you get is diffeomorphic, then if you consider projection on T star M or on Tm, in both cases, this is a section. Yeah? So this is related with the D is a section. But if Lagrangian is not regular, this is no longer true. Yeah? So you should always remember that the D could look like that. Yeah, and this is the projection. So, standard example, of course, would be very simple and elementary. Is, of course, the Lagrangian of mechanic type, which is kinetic energy and minus potential function, which I denoted with W. Yeah? So this is the most standard Lagrangian we use in schools. Yeah.
Phase dynamic is Lagrangian, or is just a case in case of Hamiltonian Lagrangian mechanic? That
so in this case, this is regular Lagrangian. So both, you see, both descriptions are possible. But in a sense, Lagrangian is probably more basic because all of of course, as long as you don't go to more sophisticated forms of generating dynamics, like generating families. Because Lagrangian Hamiltonian, single Hamiltonian, gives you always explicit equation. And if you like to work with constraints, etc., so moreover, the Lagrangian size usually has this celebrated variational picture, yeah? So you can use variational picture to say Euler-Lagrange equation.
But D is not necessarily Lagrangian.
No, in the standard case, it is. I mean, whenever you start from Lagrangian or Hamiltonian, it is.
But
it stopped to be Lagrangian submanifold when you graduate to, say, algebroids, because then in the middle you simply don't have a symplectic manifold. The tangent of Lie algebroid is not symplectic, so.
Yeah, so for instance,
it's more general.
Yeah, but on the sides, it is always Lagrange.
If you consider Euler or Poisson equations, etc., they are not associated with Lagrangian. But Lagrangian is the most simple case, standard case when we deal with standard mechanical. So of course, there are much more sophisticated ways and consistent with constraints, etc., which require much more delicate methods. This is absolutely, so to say, movie in Netflix, yeah, so everyone can watch it and see it. So I have Lagrangian like that. So the metric is as simple as possible here, yeah, because this is just Cartesian metric. Then I generated a Lagrangian submanifold by L, which is the image of this differential. So of course, in coordinates x dot, which are coordinates in T, M, and these are represented momenta, which are differentials of L with respect to, so partial derivatives of M with respect to coordinates x dot and x. So, and then I use this alpha to go back to go to the dynamics on the phase space. And of course, this is just a certain permutation of these things, and I get this. So now you have this Lagrangian submanifold in here. And this should be understood as equation, differential equation. No, but this is T of T star f. This means that if a tangent prolongation of a curve belongs to this, that means that time derivative of this is this, with I, of course, I separated the names of indices. So this should be time derivative of x, and this is by definition, in a sense, because it is x dot, and this should be time derivative of this. No, so if you write down this observation, you'll get this, which is, of course, the standard Newton equation. Yeah. But this shows how this picture, with considering only Lagrangian submanifolds and morphism of vector bundles, leads to this equation, which is the simplest case. Yeah? And this can be obtained, in this case, the Lagrangian is regular, also from Hamiltonian, which, as everyone knows, has this form. The next step is to introduce constraints into the picture. So you see, the image of differential of a Lagrangian is always a Lagrangian submanifold. But this is a fundamental observation that this can be extended to a Lagrangian defined on a submanifold, or interpreted as a constraint. So if you have a Lagrangian defined on a constraint, it also defines canonically a Lagrangian submanifold in T star Tm. Yeah, this is the definition. So you see, this means that we consider those covectors which act on vectors tangent to the constraint exactly like dl does. dl is defined on the constraint, so it acts on vector tangent to the constraint. But you see that there is a freedom here, because in a sense, all covector, I can add here any covector which annihilates the tangent bundle to the submanifold. In all this makes that this has the right dimension, and this is Lagrangian submanifold. Yeah, Lagrange multipliers. So these are Lagrange multipliers without any multipliers. But this is geometric instance of Lagrangian multiplier. And then we do the same trick, yeah? We go back to TTN and we obtain a dynamics out of it. Analogously, we can do for constraint Hamiltonian. And example is implicit dynamics of the free relativistic particle. You see, this is interesting situation because in this case, our Hamiltonian is trivial, this constraint Hamiltonian. This is a trivial, zero Hamiltonian, but defined on the constraint, which is the light cone, yeah? So actually, this is like the only constraint is responsible for the dynamics of a free massless particle. Now let's go to infinite dimension finally. So as I told you, I will consider only separable Hilbert spaces. We have a norm, and we have a corresponding Banach spaces. One is the space of bounded operator with the subnorms, which I, by analogy to finite dimension, denote just GL. And additionally, because I have a Hermitian product, here I use antilinear in the second argument, because again, this is a question of convergence. So this equation defines me out of A, defines me a dagger, which is called the Hermitian conjugation of this operator. So A is Hermitian, if it's always for bounded operator. A is Hermitian if it's the same as the dagger, anti-Hermitian. But it is a nice observation that this operator A dagger makes sense. It is properly defined not only for bounded operator on the full domain, but it's enough that this operator R is densely defined in this Hilbert space, and the domain of this dagger can be easily obtained as this one. Okay, so now with UH, I will denote this is real Banach space, subspace of the space of bounded linear operators consisting of anti-Hermitian operators. Big GL is the group of invertible elements, so isomorphism of Hilbert spaces, linear isomorphism of Hilbert spaces, and UH is the unitary group, so this is a subgroup in this complex Banachly group of elements satisfying this one. The inverse is the dagger, yeah? So again, you should be careful because, of course, this is an open subset in the space of bounded linear operations. So this is complex group. And this one is only real Banachly group. Yeah, this is written. And the Lie algebra of the unitary group is exactly the Lie algebra of anti-Hermitian operators. But, and this is again a fundamental observation, if we consider, as in Lie theory, one-parameter subgroups of a group, of a Lie group, yeah? Then we used to say that generators of this one-parameter subgroups can be interpreted as elements of the Lie algebra of this group. No, but here, we can see that if we put on U another topology, a strong topology, which is convergence when convergence on every vector, yeah? When applied to any vector, then this is no longer Banachly group or any Lie group, maybe in a reasonable sense. But this is a topological group, and we have a fundamental theorem which says that one-parameter subgroups in the unitary group with the strong topology are exactly generated by anti-self-adjoint operators. Those anti-self-adjoint means densely defined and non-bounded generally. So this is, in a sense, not a part of Banachly group theory, because the topology we consider here is the strong topology. And to go further, the next observation is that the Hilbert space, from geometric perspective, is actually a linear Kähler manifold. That is, of course, it has a complex structure, but it has a Hermitian metric and symplectic form so that they form together this Hermitian product in the Hilbert space. And the unitary group acts actually as isomorphism of both structures, yeah? Or three of them. Yeah? It preserves this Riemannian metric and this symplectic form. Therefore, I will view the complex Hilbert space as complexification of certain real Hilbert space. As I told, in standard examples, this can be done canonically. I consider functions with real values, yeah, in this L2 space or something. Then going back to the Tulczyjew triple, the phase space in this case will be the cotangent bundle of H. Because here we work with linear spaces, everything is actually trivial. T star H is H plus H star, where H is this real part of complex H. This is what. So on this real Hilbert space, we have the scalar product. And on the complex space, we can use these real coordinates, qk and pk, so that vector in this complex space with respect to certain orthonormal bases is described like that. This I will interpret as positions and this as momenta. And of course, the condition that X belongs to the Hilbert space is this one.
Definition of real part, any real Lagrangian subspace.
No, this is a real Hilbert space such that this complex is complexification of this real Hilbert space.
It's the same. Huh? That's the same.
But in a sense, this is simpler.
Yeah, it's more natural. Your definition is more natural.
H plus IH. Yeah, so
it's not unique, of course.
So I have this Riemannian metric on this complex Hilbert space with our coordinates like that. And the symplectic form is like that. So the Tulczyjew triple looks like that in this case. And this isomorphism, because everything is linear, are global, have global coordinates, and interpreting the coordinates here as qp, q dot, q dot, then I can use this coordinate as coordinates in this and this with this permutation used as isomorphism of the corresponding double vector bundle. Yeah, this is so. We can view IH as the dual of H because of this Hilbert scalar product. But what is important is that I will view this complex Hilbert space, which is complexification of my real one, as a cotangent bundle of H with this symplectic form, canonical symplectic form of the cotangent bundle, which is actually formally is written like the standard one. The only difference is the summation here is infinite, yeah, because the index k goes from 1 to infinity. So my dynamics will live here, yeah, because this is the phase space and this is the place for the dynamics. And this is a symplectic manifold with this symplectic form. But this is actually the imaginary part of the lifted pseudo-Hermitian form. This is more, maybe not so important. And because all these parts of Tulczyjew triple are canonically symplectic, with canonical isomorphisms like that, from this symplectic form, I will obtain symplectic form also here and here, which formally, if I remember how coordinates are identified, are exactly written in this. So, in our understanding now, in the quantum case, we should understand by Tulczyjew, according to Tulczyjew, our dynamics as Lagrangian submanifold in this T star H. But of course, the quantum theory is linear, so we will look for linear Lagrangian subspace. So this is definition of Lagrangian submanifold, which is formally the same as maximally isotropic. And if I have a complex linear, so an example, if I have a complex linear operator in a certain domain, so operator like that, so I consider its graph, which lies here in H plus CH, H times H, yeah, the graph sits here. And the operator is called close if this graph, this linear relation is close in this Cartesian product. This is the standard definition. But if additionally, this is Lagrangian submanifold, this is a complex linear Lagrangian submanifold here, then we will call this submanifold anti-self-adjoint relation. So you see, according to Tulczyjew, in the quantum case, we should deal with complex linear Lagrangian submanifolds in here. This is a symplectic manifold. And we have a theorem that if we have a complex linear operator, so densely, so defined on the domain D, so it is a isotropic submanifold in H times H, if and only if this operator is anti-self-adjoint. So you see, there will be close relation between anti-self-adjoint relations and anti-self-adjoint operators here. So, of course, because we deal in relations rather than with maps, so for relation, it's natural to define domain of a relation, this is clear, kernel of the relation, inverse of the relation. All this can be done similarly to the case of maps representing relation by the graphs. And this is an observation that a complex linear relation is anti-self-adjoint, and we have, these are certain theorems known from quantum theory, that the domain, but these are relations, you see, no longer operators, but formally they are saying that the orthogonal complement of domain is the kernel of the inverse relation, etc. So, but this is, from that we get that in particular, if this complex and anti-self-adjoint relation is a graph of an operator, then this can happen in and if and only if this relation is densely defined, and in this case, A must be anti-self-adjoint, which is bounded if and only if the domain is the full Hilbert space. So you see, the message is the following. If I look at complex linear anti-self-adjoint relations in this Tulczyjew T star H, then this is exactly, so any such Lagrangian submanifold is actually associated with an anti-self-adjoint operator. Now, of course, yeah.
With condition if and only if this is V is densely defined, you also need that the projection from V to the first factor is injective, no? Otherwise it cannot be a graph. When it's just a relation. For a relation to be a graph of something, it must project injectively to the first factor.
So this is an assumption. In the case where this is graph, this is exactly the condition. Of course, everything can be interpreted in terms of self-adjoint instead of anti-self-adjoint, because multiplication by I maps from self-adjoint to self-adjoint. So the message is that self-adjoint operators, densely defined and blah, 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 are exactly complex linear Lagrangian submanifolds in this product of Hilbert space. This is exact, so, and therefore they are understood as dynamics, yeah, in the quantum situation.
Closed graph. I mean, for one parameter
No,
subgroup.
in the case of Lagrangian submanifold, this is automatic because this is maximal, and closure of isotropic submanifolds is also isotropic. Yeah? So this is closeness is automatic follows from this. So consider Hilbert space, real Hilbert space, or real functions L2 on R, and the momentum operator, which is derivation of F. Domain is naturally in this L2 space W12, so functions which are differentiable and differentials are square integrable, roughly speaking. And this is anti-self-adjoint relation due to the many times used in this room fact that the partial, if you use integration by parts, yeah, this follows that this is anti-self-adjoint, because integral of the differential is 0, yeah, on real line. So traditionally, this quantum momentum operator is understood not as just the partial derivative, which is anti-self-adjoint, but as a self-adjoint operator, which is exactly on this. Okay, so I should slowly go to the end. So then I can consider quadratic Lagrangian, like in this mechanical case. Yeah? I will not go into details. Anyhow, I will use some, because I have a canonical scalar scalar product on my real Hilbert space. Of course, I can produce kinetic energy Lagrangian, etc., etc. So Lagrangian, roughly speaking, of this type. And again, we will do as in the Tulczyjew case. This is densely defined, this operator B, densely defined, defining this quadratic function. Yeah? And you remember, if I have this submanifold, linear submanifold here, I can view it as a constraint. And then to construct my Lagrangian subspace out of this constraint, and this Lagrangian defined on the constraint. So if you apply this procedure, then this is what you obtain in this linear case. Anyhow, going to the final conclusion, I have to pass to the integral part because I have a constraint, so I intersect my Lagrangian submanifold with the domain, and what I obtain is a Lagrangian submanifold associated with a certain anti-self-adjoint operator. A is self-adjoint is represents the Schrödinger operator in the Schrödinger. So just to final example, so you see I have this real Hilbert space, and I have a quadratic Lagrangian of this form. Of course, this is the domain for this Lagrangian consists of xx dots, which are functions on R, such that the square of this is integrated as finite integral, and similarly this is the natural domain of definition for this Lagrangian. And again, applying all this procedure, I obtain first this Lagrangian submanifold associated with constraint and a function on it, which is this one. And then using this, going back to the T star H interpreted as H plus H, I get this Lagrangian submanifold. But this Lagrangian submanifold is nothing but the graph of a map multiplication by T. So this is, of course, this is minus IA, where A is self-adjoint and defined by multiplication by T. So as a result, and which is self-adjoint in this domain. And there is also a Hamiltonian description for that with this Hamiltonian. And traditionally, of course, this operator, this self-adjoint operator, is called the quantum position operator. So you see, the final message is the following. We can obtain the best known quantum operators like position, quantum position, or quantum momenta out of the Tulczyjew approach to classical mechanics. So you see, all this is geometry on Hilbert spaces. And the whole idea of generating dynamics of Lagrangian and Hamiltonian is the same. Yeah? So this shows that the position, quantum position and quantum momentum operator have their Lagrangian and Hamiltonian pictures. Yeah, that's all. Thank you.